In a remote galaxy, billions of light years away, a star 100 times more massive than our sun is dying. For a brief moment, it will unleash more energy than 1 trillion suns combined, sending shockwaves across space-time itself. Tonight, we journey through cosmic forces so extreme, they bend reality to their will. We will visit explosions that outshine entire galaxies, black holes that devour light itself, and fundamental forces that hold the very fabric of existence together. Prepare yourselves for a voyage into power beyond imagination. We begin. Deep inside every atom in your body, an invisible war is raging. Protons packed together in the nucleus should tear themselves apart instantly. Their positive charges repel each other with tremendous force, like trying to push two powerful magnets together. Yet somehow they remain locked in place by the strongest force in the universe. The strong nuclear force operates at distances smaller than a single proton, but its power is absolute. Scientists measure it as 100 times stronger than electromagnetism and 100 trillion times stronger than gravity. Think of it this way: if gravity were a whisper, the strong force would be a thunderclap that could shatter mountains. This force works through particles called gluons, which act like invisible chains binding quarks together to form protons and neutrons. The more you try to pull these particles apart, the stronger the force becomes. It is like stretching a rubber band that grows thicker and more resistant with every inch you pull. This bizarre behavior, called confinement, means you can never isolate a single quark, no matter how much energy you apply. Despite each proton, 3 quarks dance in a prison of pure energy. The gluons that bind them carry the strong force itself, creating a web of interaction so complex that even our most powerful supercomputer struggle to model them. When you try to separate quarks, the energy you add simply creates new quarks and gluons, like trying to cut a chain only to have it grow new links. The strong force operates on scales so small that a femtometer seems vast. That is 1/4,000,000th of a meter, smaller than anything you could imagine. At these distances, the familiar world of everyday physics breaks down completely. Space and time themselves become uncertain, fluctuating according to the strange rules of quantum mechanics. This force shapes the very building blocks of matter. It determines which atomic nuclei can exist and which cannot. It sets the rate at which stars burn their nuclear fuel. It controls the balance between creation and destruction in the hearts of every star across the cosmic void. Without the strong force, protons would instantly fly apart due to electromagnetic repulsion. Atomic nuclei could not form. Fusion reactions and stellar cores would never begin. The universe would contain nothing but hydrogen atoms and free electrons, yet despite its incredible power, the strong force has a fatal weakness. Its reach extends only to the edge of an atomic nucleus, about 1/10,000,000th of the width of a human hair. Beyond that microscopic realm, other powers take control. Step into the wider universe, where distance means everything, and witness what happens when gravity and light collide in the most violent explosions ever detected. Somewhere in the cosmos, a beam of pure energy tears through space at nearly the speed of light. For just 10 seconds, It releases more power than our sun will produce in its entire 10 billion year lifetime. This is a gamma ray burst, and it represents the most powerful explosion the universe can create. These cosmic titans occur when the most massive stars and existence collapse into black holes. We are talking about stellar giants containing the mass of 20 to 100 suns, burning through their nuclear fuel at a rate that would consume our sun's entire energy supply in just a few million years. When these monsters finally exhaust their fusion reactions, gravity wins the ultimate battle. As the star's core implodes, it fires jets of matter and energy from its poles at 99% the speed of light. The collapsing core creates a newborn black hole surrounded by a disk of superheated material. Magnetic fields, twisted and amplified by the collapse, act like cosmic cannons, launching these jets outward with impossible precision. The jets punch through the dying star like bullets through tissue paper, emerging as focused beams of destruction that remain tightly collimated across vast distances. Think of a laser beam that maintains its focus while traveling from Earth to the nearest star. These jets accomplish something similar on scales millions of times larger. A single gamma ray burst can outshine 1 trillion stars. If you could see gamma rays with your eyes, these explosions would appear brighter than the full moon. Even from galaxies billions of light years away, the energy released in seconds exceeds what 10 trillion hydrogen bombs could produce if they exploded every second for the entire age of the universe. The most powerful gamma ray burst ever detected, nicknamed the boat for brightest of all time, occurred in October 2022. It was so intense that it saturated gamma ray detectors across the solar system and created detectable changes in Earth's upper atmosphere from a distance of 2 billion light years. Pictures standing on Earth and watching a flashlight beam from Alpha Centauri appear as bright as a car headlight that gives you a sense of how impossibly powerful these events truly are. The light we detect traveled for billions of years, carrying news of stellar deaths from when the universe was young and stars were more massive and violent than anything we see today. Scientists have detected bursts so distant. Their light began traveling when the first stars were being born less than 1 billion years after the Big Bang. These ancient beacons give us glimpses of the early cosmos, when massive stars lived fast and died violently, seating space with heavy elements essential for later generations of stars and planets. But compared to what lurks in the darkness between galaxies, even these titans pale in comparison. At the heart of our galaxies, it's a monster 4 million times more massive than the Sun. Sagittarius A star devours everything that ventures too close, from gas clouds to entire star systems. This giant is considered small compared to the true titans of the cosmic deep. Some supermassive black holes contain the mass of 40 billion suns, compressed into a region smaller than our solar system. They are like cosmic vacuum cleaners, with gravity so intense that nothing, not even light, can escape once it crosses their event horizon. Space and time bend around them like water swirling down a drain, creating distortions that would seem impossible if we did not observe them directly. These gravitational monsters did not grow slowly. The most distant quasars shine from when the universe was less than 1 billion years old, powered by black holes that somehow grew to billions of solar masses in the cosmic equivalent of a few minutes. How they achieved such impossible growth remains one of astronomy's greatest mysteries. Small stellar evolution simply cannot explain their existence. The leading theory suggests these giants began as massive seeds formed directly from collapsing gas clouds in the early universe. Unlike stellar mass black holes that form from dying stars, these primordial monsters may have contained hundreds of thousands of solar masses from the moment of their birth. This head start allowed them to grow rapidly by consuming surrounding matter and merging with other black holes. When gas spirals into a supermassive black hole, friction heats it to temperatures of millions of degrees. The material forms an accretion disk that glows brighter than 100 billion stars. The disk rotates so rapidly that matter near the inner edge travels at significant fractions of light speed, experiencing time dilation effects that would stretch seconds into hours for outside observers. The most luminous quasars powered by feeding black holes can be seen from across the observable universe, like cosmic lighthouses broadcasting their presence across billions of light years. They outshine their entire host galaxies, making the combined light of hundreds of billions of stars seem dim by comparison. The most violent black holes launch jets of particles at nearly light speed, creating beams that stretch for hundreds of thousands of light years. These jets carry enough energy to reshape entire galaxies, heating gas clouds to millions of degrees and preventing new stars from forming across vast regions of space. The jets can remain active for millions of years, continuously pumping energy into their surroundings. Recent observations have revealed black holes that seem too massive for their host galaxies, breaking the normal relationships between central black hole mass and galactic properties. These overmassive giants challenge our understanding of how galaxies and their central black holes evolved together. But even these titans bow to forces that operate on scales beyond imagination. Across 13.8 billion light years of space, an invisible force is winning a cosmic war. Every second, it pushes galaxies farther apart, stretching the very fabric of space, time itself. This mysterious power, called dark energy, makes up 70% of everything that exists, yet we know almost nothing about what it actually is. Dark energy is not like other forces. It does not weaken with distance, like gravity or electromagnetism. Instead, as space expands, more dark energy appears to fill the void. The bigger the universe becomes, the faster it expands. It is like a cosmic gas pedal that only knows how to accelerate, growing stronger as it pushes everything apart. Space discovered this force by accident while studying distant supernovae in the 1990s. They expected the universe's expansion to be slowing down due to the gravitational pull of all the matter within it. Instead, they found the opposite. Space is expanding faster today than it was billions of years ago, as if some invisible hand is pulling everything apart with increasing strength. Think of the universe as a balloon being inflated by an invisible breath. Dark energy is that breath. It is causing every point on the balloon's surface to move away from every other point. Galaxies ride this expanding space like boats on a swelling ocean, powerless to resist the tide that carries them into the cosmic deep. The amount of dark energy in the universe increases as space expands. This seems to violate conservation of energy, one of the most fundamental laws of physics. Yet observations consistently show that the energy density of dark energy remains constant, even as the volume of space grows. Where this extra energy comes from remains completely unknown. Current theories suggest dark energy might be a property of space itself, a kind of cosmic constant that Einstein originally proposed and later called his greatest blunder. Others think it could be a dynamic field that changes over time, or even evidence that our understanding of gravity needs major revision on cosmic scales. The consequences of dark energy are profound and terrifying. In the far future, it will tear apart everything we see. First, galaxy clusters will separate beyond recognition, becoming isolated islands in an ocean of expanding darkness. Then, individual galaxies will lose their ability to hold together against the cosmic expansion. Eventually, even atoms themselves may be stretched apart in what scientists call the Big Ipe. Stars will be extinguished, planets will drift away from their suns, and even the fundamental particles that make up matter will be separated by vast distances. Dark energy, which seems gentle today, will become the universe's final destroyer, unmaking everything that gravity and the other forces worked billions of years to create. Imagine taking a mountain and compressing it down to the size of a sugar cube. The result would still be 1,000 times less dense than a neutron star. These cosmic lighthouses pack the mass of our sun into a sphere just 12 miles wide, creating gravitational fields so intense they warp light itself and bend space-time into impossible geometries. But gravity is not their most terrifying feature. Neutron stars possess magnetic fields 1 trillion times stronger than Earth's protective magnetosphere. These invisible force fields trap charged particles and accelerate them to nearly the speed of light, creating beams of radiation that sweep across space like cosmic searchlights powered by the fundamental forces of the universe. The magnetic field of a typical neutron star is so powerful it could erase every credit card on Earth from a distance of 600 miles. If you could somehow approach within 1,000 kilometers, the magnetic force would be strong enough to pull the iron from your blood. The field lines themselves become visible as they trap and channel streams of charged particles into narrow beams. When these magnetized neutron stars spin, they become pulsars, firing beams of radio waves and X-rays with the precision of atomic clocks. Some rotate 600 times per second, faster than a kitchen blender, yet maintain perfect timing that rivals the most accurate timepieces ever built. Each pulse marks another rotation of a stellar corpse spinning in the darkness. The surface of a neutron star is a realm of impossible physics where familiar matter cannot exist. The magnetic field is so strong it stretches atoms into needle-like shapes aligned with the field lines. Normal atomic structure breaks down completely, replaced by exotic forms of matter that exist nowhere else in the universe. Any ordinary matter that falls onto a neutron star's surface would be compressed instantly into a layer just millimeters thick. The gravity is so intense that a marshmallow dropped from waist height would hit the surface with the force of a hydrogen bomb, releasing more energy than all the explosives used in World War II. Some neutron stars, called magnetars, have magnetic fields 1,000 times stronger still, approaching the maximum strength allowed by the laws of physics. When these objects experience magnetic quakes, their crusts crack and shift, releasing more energy in 1/10 of a second than our sun produces in 100,000 years. These magnetic cataclysms create giant flares that can be detected from across the galaxy. The most powerful magnetar flare ever recorded temporarily affected Earth's upper atmosphere from a distance of 50,000 light years, demonstrating the incredible reach of these stellar remnants. The magnetic field around a magnetar is so intense that it affects the vacuum of space itself, causing it to become biofringent like a crystal. Light waves become polarized as they pass through this magnetized void, providing astronomers with direct evidence of field strengths that exceed anything achievable in terrestrial laboratories. But these stellar remnants are only the beginning of nature's most extreme creations. Stretching across the observable universe are invisible threads that could slice through planets like wire through cheese. These cosmic superstrings, if they exist, are one-dimensional objects thinner than a proton, but potentially longer than galaxy clusters. They are scars left over from the birth of the universe itself, marking phase transitions in the fundamental structure of space-time. According to string theory, cosmic strings formed during the first fraction of a second after the Big Bang, when the universe underwent rapid changes in its fundamental properties. They are like cracks in a frozen pond, marking the boundaries where different regions of space crystallized in slightly different ways as the cosmos cooled from its initial state of perfect symmetry. A cosmic string just 1 meter long would weigh as much as Earth. Yet these objects are so thin, they are essentially one-dimensional, having length but no width or height in the conventional sense. They exist at the very boundary between existence and nothingness, matter and energy, reality and pure mathematics made manifest. The energy contained within a cosmic string is almost incomprehensible. A string spanning the distance from Earth to the Moon would contain enough mass energy to power human civilization for trillions of years. Yet this enormous energy is concentrated in a line so thin that it has no measurable thickness, making cosmic strings the ultimate expression of energy density. If cosmic strings move through space, they create ripples in space, time itself, generating gravitational waves that could be detected by our most sensitive instruments. These waves would have a unique signature, different from those produced by black hole mergers or neutron star collisions, allowing scientists to potentially confirm the existence of these theoretical objects. When two cosmic strings intersect, they can create loops that oscillate like guitar strings plucked by the hand of the universe itself. But instead of producing sound waves, these vibrating loops generate distortions in the fabric of reality, sending gravitational waves rippling outward at the speed of light. These cosmic string loops gradually lose energy through gravitational wave radiation, shrinking over time until they eventually disappear. A loop the size of our solar system would radiate away all its energy in just a few million years, vanishing in a final burst of space-time distortion. Some scientists believe cosmic strings could act as cosmic highways, allowing faster-than-light travel through folded space. If 2 points in space were connected by a cosmic string, you could theoretically travel along the string and arrive at your destination before light traveling through normal space. This would make cosmic strings the universe's ultimate shortcuts. Others think cosmic strings might be windows into extra dimensions hidden from our three-dimensional world. The strings could be fundamental mental objects that exist in higher dimensional space, with only their one-dimensional cross-sections visible in our reality. These theoretical monsters remain hidden in the mathematics of physics, waiting to be discovered or disproven by future observations. 4 billion light years from Earth, a black hole the size of our solar system is launching a beam of particles that stretches across an entire galaxy. This jet of superheated plasma moves at 99.9% the speed of light, carrying enough energy to power 1 trillion stars, while maintaining perfect focus across distances that dwarf human comprehension. Quasar jets are born in the chaos surrounding supermassive black holes, where space-time itself becomes a battlefield between gravity and magnetism. As matter spirals inward towards certain doom, it forms an accretion disk, spinning at incredible velocities. Magnetic fields amplified by the disk's rotation become twisted into configurations that store enormous amounts of energy. These magnetic field lines act like cosmic particle accelerators, channeling material from the inner regions of the accretion disk into narrow beams that shoot outward from the black hole's poles. The same gravitational forces that should drag everything into oblivion instead launch some material back into space at relativistic speeds through this magnetic catapult mechanism. The jets are so straight they appear drawn with a cosmic ruler held by divine hands. They maintain their narrow focus across distances of hundreds of thousands of light years, threading through space with precision no human technology could match. The collimation is so perfect that jets observed with radio telescopes appear as thin lines, even when viewed from billions of light years away. The particles within these jets carry energies millions of times greater than anything we can create in our most powerful particle accelerators on Earth. Several protons race along the jet at speeds so close to light that their relativistic mass increases by factors of thousands, turning ordinary matter into cosmic bullets of incredible power. When a quasar jet points directly at Earth, we see it as a blizzard, and the light appears to brighten and fade as the beam sweeps past us like a lighthouse. These blazers can vary in brightness by factors of hundreds within days or hours, as turbulence in the jet creates bright knots of emission traveling toward us at apparent speeds faster than light itself. This faster than light motion is an illusion created by the geometry of observation. When material moving at 99% light speed travels almost directly toward us, it appears to cover vast distances in impossibly short times. The effect demonstrates just how close to the ultimate speed limit these cosmic jets actually travel. The most powerful quasar jets carry enough energy to heat entire galaxy clusters, blowing bubbles in the surrounding gas that persist for hundreds of millions of years. These cosmic blow torches can prevent new stars from forming across regions spanning millions of light years, effectively sterilizing vast volumes of space. Recent observations have revealed jets that extend far beyond their host galaxies, stretching into the intergalactic medium where they continue to propagate for millions of years. These ancient jets carry the signature of black hole activity from cosmic epochs when the universe was younger and more violent than today, in a binary star system 30 million light years away. A white dwarf star is slowly stealing material from its companion like a cosmic vampire feeding on stellar blood. For millions of years, hydrogen gas flows from the largest star onto the compact remnant, building up layer by layer like snow accumulating on a mountainside. But this stellar snowball is approaching a deadly threshold that will trigger one of the universe's most precise explosions. White dwarf stars are the dense cores left behind when sunlight stars exhaust their nuclear fuel and shed their outer layers. These stellar remnants pack the mass of our Sun into a sphere the size of Earth, creating matter so dense that a teaspoon would weigh as much as a car. Their surface is burned at temperatures of tens of thousands of degrees, hot enough to vaporize any known material. The stolen material accumulates on the white dwarf's surface, compressed by gravity into a thin shell of hydrogen that gradually builds up pressure and temperature. The white dwarf acts like a cosmic pressure cooker, slowly heating this stolen matter until nuclear fusion begins to smolder in the surface layers. When the white dwarf reaches exactly 1.4 times the mass of our Sun, something catastrophic happens. This critical mass, known as the Chandrasekhar limit, represents the maximum weight that electron degeneracy pressure can support. Beyond this point, the star can no longer hold itself up against its own gravity. The accumulated material ignites in a runaway thermonuclear explosion that tears the entire star apart in seconds. The explosion propagates through the white dwarf like a flame front racing through cosmic dynamite, converting carbon and oxygen nuclei into iron and nickel through explosive nuclear fusion. The star literally burns itself out of existence. This is a Type Ia supernova, and it represents one of the most precisely violent events in the universe. Every Type A supernova releases almost exactly the same amount of energy because they all involve the same mass of material undergoing the same nuclear reaction. This cosmic standardization makes them perfect tools for measuring distances across billions of light years. The explosion shines with the light of 5 billion suns, visible from galaxies billions of light years away. For weeks, a single exploding white dwarf can outshine an entire galaxy containing hundreds of billions of normal stars. The brightness peaks quickly and then fades over months as radioactive elements created in the explosion decay and release their energy. The explosion synthesizes and scatters elements essential for life across vast regions of space. The calcium in your bones, the iron in your blood, and the nickel and coins were all forged in the hearts of exploding white dwarf stars. You are literally made of stellar ashes scattered by these cosmic crematoriums billions of years ago. The shock wave from a supernova travels outward at thousands of miles per second, heating surrounding gas to temperatures of millions of degrees. The explosion can trigger new waves of star formation in nearby gas clouds, while simultaneously enriching them with heavy elements necessary for planetary formation. Two city-size objects spiral toward each other through the darkness of space, locked in a gravitational dance that has lasted for millions of years. They are neutron stars, the crushed cores of massive stars, and their collision will create the most violent event in the nearby universe, while forging elements more precious than anything in a king's treasury. Each neutron star contains more mass than our sun compressed into a sphere just 12 miles across. Their surfaces are made of atomic nuclei crushed together so tightly that a single teaspoon would weigh 6 billion tons on Earth. These are not ordinary objects, but rather the densest forms of matter that can exist without collapsing into black holes. As they orbit closer and closer, the neutron stars distort each other's shapes through pure gravitational force. Tidal forces stretch and squeeze these incredibly dense objects like cosmic taffy, generating heat that makes their surfaces glow with temperatures of millions of degrees. The orbital dance accelerates as energy bleeds away through gravitational waves. These gravitational waves carry away orbital energy at an ever-increasing rate, causing the neutron stars to spiral inward faster and faster. The waves themselves are ripples in space-time, stretching and compressing the very fabric of reality as they race outward at light speed. Advanced detectors on Earth can measure these waves even though they change distances by less than 1/10,000th of a proton. In the final seconds before collision, the neutron stars complete hundreds of orbits per second, whirling around each other faster than a helicopter blade. The gravitational waves they generate become so powerful they carry away the energy equivalent of 3 sun masses in just the last few seconds before impact, causing the death spiral to accelerate exponentially. When the neutron stars finally touch, they create a brief flash of gamma rays, followed by a longer, lived explosion called a kilonova. The collision is so violent, it literally shakes the universe, sending gravitational wave signals that can be detected from billions of light years away by sensitive instruments designed to measure the impossible. The merger forges elements heavier than iron through a process called rapid neutron capture. In the extreme conditions of the collision, atomic nuclei are bombarded with so many neutrons that they can barely absorb them fast enough. This creates unstable neutron-rich isotopes that decay into stable heavy elements, including gold, platinum, and uranium. A single neutron star merger produces quantities of gold equivalent to several Earth masses, along with comparable amounts of other precious metals. The collision ejects this stellar treasure at speeds approaching 1/3 the speed of light, seeding nearby space with materials that will eventually find their way into future generations of planets and asteroids. The collision ejects material in multiple components, moving at different speeds. The fastest moving debris creates the initial gamma-ray burst, while slower material forms expanding shells that glow with radioactive decay for weeks afterward. This kilonova light comes from billions of newly created atomic nuclei undergoing radioactive decay, creating a fireball that shines with the combined light of hundreds of millions of suns. 13.8 billion years ago, everything that exists today was compressed into a point smaller than a proton. All the matter and energy in the observable universe, from the smallest quantum particles to the largest galaxy clusters, occupy the space with no dimensions at all. This was the Big Bang singularity, and it represents the ultimate expression of cosmic power, the moment when existence itself began. At this primordial moment, the laws of physics, as we understand them, break down completely. Temperature and density become infinite. Space and time have no meaning. The four fundamental forces that govern everything in the modern universe were unified into a single, unimaginably powerful interaction that held sway over reality itself. In the first fraction of a second, smaller than the time it takes light to cross a proton, the universe expanded faster than light itself. This period of cosmic inflation stretched space by factors of billions in less time than it takes to blink. Space did not explode into pre-existing emptiness, but rather created new space as it grew, carrying matter and energy along for the ride. The temperature during these first moments was so high that even the fundamental forces of nature could not maintain their separate identities. Gravity, electromagnetism, and the strong and weak nuclear forces were indistinguishable aspects of a single super force that has never existed since those first instants of creation. As the universe expanded and cooled, this cosmic unity shattered like glass cooling too quickly. The forces separated in a series of phase transitions that released enormous amounts of energy and determined the basic structure of physical law. This gravity separated, then the strong force, and finally, electromagnetism split from the weak force. During the first minute after the Big Bang, the universe cooled enough for the first atomic nuclei to form through a process called Big Bang nucleosynthesis. Protons and neutrons, newly formed from cooling quarks, fused together in a cosmic forge that created most of the hydrogen and helium we see today. The energy density was so extreme that matter and antimatter annihilated each other in constant flashes of pure energy. For 300 Zarrozen years after the initial explosion, the universe remained opaque to light. Free electrons scattered photons so efficiently that light could travel only tiny distances before being absorbed and re-emitted. The cosmos was like a glowing fog filled with energy, but impossible to see through. Then came cosmic dawn. This is an atomic nuclei finally combined to form the first neutral atoms, allowing light to travel freely for the first time. This cosmic clearing created the afterglow we still see today as the cosmic microwave background radiation, a faint echo of creation itself that fills every corner of the sky. The Big Bang was not an explosion in space, but an explosion of space itself. It created time as well as matter, establishing the laws of physics that govern everything from quantum fluctuations to galaxy formation. No event before or since has matched its power to create everything from nothing to establish the very foundations of existence. And yet, even this cosmic genesis may not represent the ultimate limit of power in our universe. Beyond the realm of ordinary supernova lies something far more violent. When a star containing 50 times the mass of our Sun finally runs out of nuclear fuel, it does not simply collapse and explode. Instead, it creates a hypernova, an explosion so energetic it dwarfs regular supernova by factors of 10 to 100, releasing the energy equivalent of billions of atomic bombs detonating every second for millions of years. These stellar monsters are rare even on cosmic time scales. Only the most massive stars in the universe can trigger hypernovae, and they must be spinning rapidly when they die. The combination of extreme mass and rotation creates conditions so violent that normal stellar death cannot contain the fury about to be unleashed. When the core of such a star collapses, it forms a black hole almost instantly, but the star's rapid rotation prevents a simple, symmetric collapse. Instead, the infalling material creates an accretion disk around the newborn black hole, spinning so fast it becomes a cosmic dynamo, generating magnetic fields of unimaginable strength. These twisted magnetic field lines act like springs wound to the breaking point. When they finally snap and reconnect, they launch jets of matter and energy outward. At 99.9% the speed of light, these jets bore through the collapsing star like cosmic drill bits, carrying enough energy to power our Sun for billions of years. The jets punch through the star's outer layers and burst into space. During the gamma ray bursts, we detect from billions of light years away. But the violence does not end there. The shock wave from the jet's passage heats the star's interior to temperatures exceeding those in the cores of normal stars, triggering explosive nuclear burning throughout the stellar remnant. Layer after layer of the star explodes outward in a cascade of thermonuclear violence. Carbon burns to neon, neon burns to silicon, and silicon burns to iron in a matter of seconds. The energy released by these rapid fusion reactions adds to the destruction, creating an explosion that can be seen from the edge of the observable universe. A single hypernova can synthesize more heavy elements than dozens of normal supernovae. The extreme conditions create radioactive isotopes that decay over weeks and months, powering an afterglow that continues long after the initial explosion. These cosmic forges produce many of the elements essential for life, scattering them across vast regions of space. The most powerful hypernovae can disrupt star formation across entire regions of galaxies. Their shock waves compress nearby gas clouds, triggering new waves of stellar birth, while simultaneously heating the surrounding medium to temperatures that prevent further star formation for millions of years. Across hundreds of millions of light years of space, two massive galaxy clusters race toward each other at speeds of thousands of miles per second. Each cluster contains thousands of galaxies, trillions of stars, and vast oceans of superheated gas that glow with X-ray light. When these cosmic titans collide, they create the most energetic events in the universe since the Big Bang itself. Galaxy clusters are the largest gravitationally bound structures in the cosmos. The Coma cluster alone contains over 1,000 galaxies and has a total mass equivalent to 100 trillion suns. When clusters of this magnitude collide, the energy released exceeds the combined output of all the stars in both clusters by factors of million. The collision begins slowly by cosmic standards, but the clusters approaching each other over hundreds of millions of years. Dark matter, which makes up most of each cluster's mass, feels only the pull of gravity and passes through the collision relatively unaffected, with the hot gas that fills the space between galaxies experiences a very different fate. As the clusters merge, their gas clouds slam into each other at velocities approaching 5,000 miles per second. The collision creates shock waves that heat the gas to temperatures exceeding 100 million degrees, hot enough to strip electrons from any atom. The resulting plasma glows brilliantly in X-rays, creating some of the most luminous objects in the universe. These cosmic crashes can trigger the formation of radio halos spanning millions of light years. Magnetic fields, stretched and amplified by the collision, accelerate electrons to near light speed, causing them to emit radio waves as they spiral around field lines. The result is a ghostly radio glow larger than entire galaxies. The most violent cluster collisions can create bow shocks that propagate outward at thousands of kilometers per second. These cosmic sonic booms compress and heat the surrounding medium, creating structures visible across vast distances. The energy contained in these shocks exceeds the total energy output of billions of supernovae. During the collision, individual galaxies within the clusters experience their own violent encounters. Tidal forces can strip stars from galaxy outskirts, creating long streams of stellar debris that trace the cluster's gravitational dance. Large galaxies may be completely disrupted, their stars scattered into the growing cluster's halo. The collision can trigger massive bursts of star formation as gas clouds within galaxies are compressed by the encounter. These star bursts can increase a galaxy's star formation rate by factors of hundreds, creating brilliant blue regions filled with newly born massive stars that will live fast and die young. Hidden in the quantum foam that underlies all reality lurks a possibility so terrifying that it could end everything we know in an instant. The Higgs field, which gives all particles their mass, might not be in its lowest possible energy state. If this field suddenly dropped to its true minimum, it would create a bubble of destruction that expands at light speed, rewriting the laws of physics and annihilating everything in its path. The Higgs field permeates every corner of space, existing even in the vacuum between atoms. Like a ball balanced on a hill, this field might currently sit in what physicists call a false vacuum state. It appears stable, but it could potentially roll down to an even lower energy level, fundamentally changing the nature of reality itself. If vacuum decay began anywhere in the universe, it would create an expanding sphere of true vacuum, moving outward at exactly the speed of light. Nothing could escape this cosmic wave of destruction because no information or matter can travel faster than light. We would have no warning of its approach until the moment it arrived. Inside the bubble of true vacuum, The fundamental constants of nature would be different. Particles might have different masses or might not exist at all. Atoms as we know them could not form. The strong nuclear force might be weaker, causing all atomic nuclei to fall apart instantly. Chemistry and biology would become impossible. The energy difference between the false vacuum and true vacuum would be released as the bubble expanded. This energy could exceed the rest mass energy of all matter in the universe, making vacuum decay more energetic than converting every proton, neutron, and electron into pure energy. The universe would be flooded with more power than every star in galaxy combined. Current calculations suggest that our vacuum might indeed be metastable, balanced precariously on the edge of stability. High-energy events like cosmic ray impacts or black hole evaporation could potentially trigger the transition. Even quantum fluctuations might spontaneously nucleate a bubble of true vacuum in empty space. The terrifying aspect of vacuum decay is its inevitability if the false vacuum state exists. Quantum mechanics guarantees that any metastable state will eventually decay, even if the probability is incredibly small. Over the vast timescales of cosmic evolution, even the most unlikely events become certain. Vacuum decay would be the ultimate cosmic reset button. Everything that has ever existed, every star, planet, and living being would be erased and replaced by a universe with fundamentally different physics. No trace of our current reality would remain, not even the memory that it had ever existed. Some theories suggest that vacuum decay might have occurred multiple times in our universe's history, with each transition creating new regions with different physical laws. We might be living in just one bubble among many, surrounded by realms where the rules of existence are utterly alien. In the first moments after the Big Bang, when the universe was smaller than an atom and denser than the core of a neutron star, tiny fluctuations in density could have collapsed to form black holes, more massive than mountains, yet smaller than atoms. These primordial black holes would possess gravitational fields so intense they warp space and time on scales invisible to the human eye. Unlike black holes formed from collapsing stars, primordial black holes could have any mass. Some might weigh as little as a paperclip, while others could exceed the mass of our sun. The smallest ones would be quantum objects, where the strange rules of quantum mechanics clash with the absolute authority of general relativity in ways we barely understand. A primordial black hole with a mass of a mountain would be smaller than a proton, yet possess a gravitational field millions of times stronger than anything we can create on Earth. Space and time around such objects would be twisted into impossible geometries, creating regions where the familiar concepts of distance and duration lose all meaning. These microscopic monsters would be among the most violent objects in the universe. According to Stephen Hawking's calculations, black holes emit radiation and slowly evaporate over time. The smaller the black hole, the faster it evaporates and the more violently it dies. Primordial black hole with a mass of a large asteroid would explode with the energy of millions of hydrogen bombs. The final moments of a small primordial black hole's life would be spectacular beyond imagination. As it shrinks to subatomic sizes, the rate of evaporation accelerates exponentially. In its last second of existence, it would release more energy than our sun produces in an entire year, all concentrated in a point smaller than an atomic nucleus. If primordial black holes exist in large numbers, they could solve one of cosmology's greatest mysteries, the nature of dark matter. These invisible objects would exert gravitational influence without emitting light, exactly matching the properties astronomers observe in dark matter throughout the universe. The search for primordial black holes has led scientists to examine some of the most extreme environments in the cosmos. When these objects pass through stars, they would heat the stellar material and cause detectable changes in brightness. When they collide with neutron stars, they might trigger observable gravitational wave signals. Some primordial black holes might have grown over cosmic time by creating matter and merging with other black holes. These objects could now be lurking in the dark spaces between stars, invisible predators waiting to encounter matter they can devour. Their gravitational lensing effects might occasionally bend and magnify light from distant stars. The most massive primordial black holes could have served as seeds for the supermassive black holes we observe at the centers of galaxies today. This would solve the puzzle of how such enormous black holes could have formed so early in the universe's history, when normal stellar evolution had barely begun. Before the universe was even 1 second old, space itself underwent the most violent expansion in cosmic history. In a period shorter than the time it takes light to cross a proton, the universe grew from smaller than an atom to larger than a grapefruit. This process, called cosmic inflation, represents the most powerful force ever unleashed, stretching space faster than the speed of light and setting the stage for everything that followed. During inflation, space expanded by a factor of at least 10 to the 26th power in just 10 to the negative 35 seconds. To put this in perspective, imagine a single atom suddenly growing larger than our solar system in less time than it takes light to travel the width of that atom. This expansion was so rapid it defies human comprehension. The driving force behind inflation was a quantum field called the inflaton, which filled all of space with an enormous energy density. Unlike normal matter, this field had the bizarre property of creating more energy as space expanded, acting like a cosmic fuel that never ran out. The more the universe grew, the more energy became available to drive further expansion. Inflations solved several fundamental problems that had puzzled cosmologists for decades. For inflation, the universe would have been filled with exotic particles and topological defects that should still be observable today. The rapid expansion stretched these objects to sizes larger than the observable universe, effectively hiding them beyond our cosmic horizon. The expansion during inflation was so extreme that regions of space that were initially in contact were stretched far beyond any possibility of communication. This explains why the cosmic microwave background radiation has nearly identical temperatures in all directions, even though these regions could never have exchanged energy after the expansion began. Quantum fluctuations in the inflaton field during inflation were stretched to cosmic scales, creating the density variations that would later grow into galaxies and galaxy clusters. These tiny ripples in the fabric of space-time became the seeds of all large-scale structure in the universe, from the smallest stars to the largest superclusters. The amount of energy involved in cosmic inflation was truly staggering. In just a tiny fraction of a second, the inflatoned field released more energy than has been produced by every star in the observable universe over the past 13.8 billion years. This energy went into creating new space and filling it with the matter and radiation we see today. When inflation finally ended, the inflaton field decayed into ordinary matter and radiation, reheating the universe to temperatures exceeding 10 to 28 degrees. This was hot enough to create and destroy particles at rates that would make the cores of the most massive stars seem frigidly cold by comparison. Some theories suggest that inflation did not occur just once, but is an eternal process that continues to create new regions of space-time beyond our observable universe. In this scenario, our entire cosmos might be just one bubble in an infinite multiverse where new universes are constantly being born through inflation. In the heart of a dying star spinning at 1,000 revolutions per second, magnetic fields 1 trillion times stronger than Earth's are about to unleash destruction beyond imagination. This is a magnetorotational supernova where the combination of extreme rotation and magnetic power creates explosions that dwarf even the mightiest gamma-ray bursts. Emerging magnetic fields so intense they could tear apart atomic nuclei from thousands of miles away. When the most massive stars in the universe reach the end of their lives, some possess magnetic fields comparable to those found on magnetars. If such a star is also rotating rapidly when its core collapses, the conservation of angular momentum spins the collapse even faster. Like a figure skater pulling in their arms during a pirouette, as the stellar core shrinks from the size of Earth to just 12 miles across, its rotation rate increases by millions of times. The magnetic field lines, frozen into the collapsing plasma, become twisted and amplified until they reach strengths that approach the theoretical limits allowed by physics. These fields become so powerful they can influence the structure of space-time itself. The magnetic pressure in these extreme fields exceeds the pressure inside atomic nuclei. Field lines stretched to the breaking point store enough energy to power our sun for billions of years. When these magnetic structures finally become unstable and reconnect, they release this stored energy in violent magnetic explosions that make solar flares seem like gentle breezes. The combination of rapid rotation and extreme magnetic fields creates a cosmic dynamo more powerful than anything else in the universe. Charged particles caught in these fields are accelerated to energies far exceeding anything achievable in our most advanced particle accelerators. Individual protons gain enough energy to split atomic nuclei through pure kinetic impact. These magnetorotational explosions can launch jets of magnetized plasma at velocities approaching the speed of light. Unlike the jets from ordinary gamma-ray bursts, these magnetically driven outflows maintain their focus across intergalactic distances, creating beams of destruction that could sterilize planets from millions of light years away. The magnetic fields generated during these explosions are so strong they affect the vacuum of space itself. At field strengths exceeding 10 to the 15th Gauss, the quantum vacuum becomes birefringent, splitting light into separate polarizations and creating optical effects that exist nowhere else in the universe. Space itself becomes a kind of cosmic crystal with directional properties. Matter exposed to these extreme magnetic fields experiences effects that seem impossible by everyday standards. Atoms become elongated into needle-like shapes aligned with the field. The chemical bonds that hold molecules together are twisted and distorted beyond recognition. Even the fundamental particles that make up atoms begin to behave in strange new ways. The energy released by a magnetorotational supernova can exceed that of a normal supernova by factors of hundreds. The explosion synthesizes exotic isotopes that cannot be created under any other conditions, forging elements that exist for mere seconds before decaying into more stable forms. These cosmic alchemical laboratories create materials that push the boundaries of nuclear physics. In the vast halos surrounding every galaxy, an invisible substance outweighs all the stars by factors of 5 to 1. This dark matter feels gravity, but interacts with nothing else we understand, creating a shadow universe that shapes cosmic structure while remaining completely hidden from our eyes. But if dark matter particles ever encounter their anti-matter twins, they could unleash explosions that make supernovae look like fireflies. Dark matter particles, if they are their own antiparticles, would annihilate completely when they collide, converting their entire mass into pure energy, according to Einstein's famous equation. A single kilogram of dark matter undergoing annihilation would release the same energy as 21 million tons of explosives, making it the most efficient energy source theoretically possible. In the dense cores of galaxy clusters, where dark matter concentrations reach their peak, these annihilation events could create cascades of high-energy particles and gamma rays. The energy released would exceed the combined output of all the stars in the cluster, creating radiation so intense it could be detected from billions of light years away. Some theories suggest that dark matter particles could be much more massive than ordinary protons and neutrons, potentially containing the energy equivalent of hundreds or thousands of hydrogen atoms compressed into a single particle. When such massive particles annihilate, they would create particle showers of incredible energy, producing cascade reactions that generate exotic particles found nowhere else in nature. The annihilation process could create pairs of photons with energies millions of times greater than visible light. These gamma rays would carry the signature of dark matter destruction, providing a direct window into the properties of this mysterious substance. The most energetic annihilation events could produce photons with energies approaching the Planck scale, where quantum gravity effects become important. If dark matter annihilation occurs preferentially in high-density regions, it could create feedback effects that shape the distribution of matter on cosmic scales. The energy released could heat nearby gas, preventing it from collapsing to form new stars. Entire regions of galaxies might be sterilized by the radiation from dark matter annihilation in their central regions. In the extreme environment near black holes, where dark matter densities can reach extraordinary levels, annihilation rates could become so high that they contribute significantly to the total energy output. These events might create observable signatures in the form of high-energy neutrinos or gamma-ray flares that could reveal the presence of dark matter concentrations. Some theoretical models predict that dark matter annihilation could trigger chain reactions where the energy released creates conditions favorable for further annihilation events. These cascading annihilations could empty entire regions of space of their dark matter content, leaving behind cosmic voids filled with high-energy radiation. The search for dark matter annihilation signals has led astronomers to examine the most extreme environments in the universe. Galaxy centers where dark matter densities peak are prime targets for detecting the tail gamma ray signatures of annihilation. The absence of clear signals so far suggests that either dark matter does not self-innulate, or the process occurs much more rarely than initially predicted. Somewhere in the depths of space, protons are being accelerated to energies that dwarf anything we can achieve on Earth. These cosmic ray particles race through the galaxy at 99.99999% the speed of light, carrying individual energies equivalent to a baseball thrown at 60 miles per hour compressed into a single atomic nucleus. The cosmic accelerators that create these particles operate on scales and with efficiencies that make our most advanced technology seem primitive. The most energetic cosmic rays detected on Earth carry energies exceeding 10 to the 20th electron volts, more than 10 million times the energy achievable in the Large Hadron Collider. A single one of these particles contains enough energy to light a small bulb for a brief moment, all concentrated in an object smaller than a proton. When such particles strike Earth's atmosphere, they create cascades of secondary particles that can trigger detectors spread across thousands of square miles. The cosmic accelerators responsible for these extreme particles remain one of astrophysics' greatest mysteries. Supernova shock waves can accelerate particles to high energies, but they cannot explain the most extreme cosmic rays. The electric fields required to accelerate particles to such energies would need to extend across distances of millions of light years and maintain voltages exceeding 10 to the 20 volts. Active galactic nuclei powered by supermassive black holes represent the most likely cosmic accelerators. The magnetic fields near these objects can store enormous amounts of energy, releasing it in sudden bursts that accelerate particles to relativistic speeds. The jets launched by these black holes create natural particle accelerators millions of light years long, far exceeding any human-built machine. When cosmic ray particles travel through magnetic fields in space, they are deflected and scattered, making it nearly impossible to trace them back to their sources. Only the most energetic particles, those with energies exceeding 10 to the 19th electron volts, travel in nearly straight lines through galactic magnetic fields. These ultra High-energy particles provide our only direct probes of the most extreme acceleration processes in the universe. The interaction of cosmic rays with magnetic fields creates some of the most spectacular phenomena in astrophysics. When these particles spiral around field lines, they emit synchrotron radiation that glows across the electromagnetic spectrum. The radio emission from our galaxy is largely produced by cosmic ray electrons spiraling through the Milky Way's magnetic field. Cosmic ray acceleration can occur through multiple mechanisms, each operating on different scales and producing particles with different energies. Shockwave acceleration occurs when particles repeatedly cross shock fronts, gaining energy with each crossing. Magnetic reconnection can accelerate particles impulsively when twisted field lines suddenly snap and reconfigure themselves. The most extreme cosmic ray events might involve entirely different acceleration mechanisms that we have not yet discovered. Some theories suggest that the decay of exotic particles left over from the Big Bang could produce cosmic rays with energies exceeding anything possible through conventional acceleration. These hypothetical particles could be relics of physics beyond the standard model. Cosmic ray interactions with gas and dust in space create secondary particles, including gamma rays, neutrinos, and positrons. These secondary products carry information about both the cosmic rays themselves and the environment through which they travel. The study of cosmic ray secondaries has revealed the composition and structure of the interstellar medium in ways impossible through direct observation. In the apparently empty space between atoms, between planets, between stars, the quantum vacuum seeds with invisible activity. Virtual particles pop into existence and annihilate each other. In time so brief they exist below the threshold of direct observation. Yet these quantum fluctuations, operating on the smallest possible scales, contain enough energy to power the entire observable universe and may ultimately determine the fate of reality itself. The quantum vacuum is not truly empty, but filled with zero-point energy that exists even at absolute zero temperature. Every cubic centimeter of space contains virtual photons, electron-positron pairs, and countless other particle combinations that borrow energy from the vacuum and must pay it back before quantum mechanics notices the violation. This constant creation and destruction of virtual particles creates an energy density that, if it could be extracted, would exceed the mass energy of all matter in the universe. Calculations suggest that the energy density of quantum vacuum fluctuations should be 10 to the 120 times 20 times larger than the observed energy density of the universe. This enormous discrepancy, known as the cosmological constant problem, represents one of the greatest failures of theoretical physics. If these calculations were correct, space itself would be so energetically unstable that atoms could not exist. Yet, quantum vacuum fluctuations do produce measurable effects that confirm their reality. The Casimir effect demonstrates that two metal plates placed very close together will be pushed toward each other by the pressure of virtual particles. The space between the plates excludes certain wavelengths of virtual photons, creating an imbalance that generates a tiny but detectable force. Virtual particles near the event horizons of black holes can become real through a process discovered by Stephen Hawking. One member of a virtual particle pair can fall into the black hole while the other escapes, causing the black hole to slowly evaporate. This Hawking radiation represents the conversion of vacuum energy into real particles, demonstrating the tremendous power contained within quantum fluctuations. In the early universe, quantum vacuum fluctuations were stretched to cosmic scales during the period of inflation. These microscopic energy variations became the seeds of all large-scale structure, growing under the influence of gravity to form the galaxies and galaxy clusters we observe today. Every star, planet, and living being owes its existence to quantum fluctuations that occurred when the universe was smaller than an atom. Some theories suggest that our entire universe originated from a quantum vacuum fluctuation, a brief deviation from nothingness that somehow became permanent. In this scenario, the Big Bang itself was not the beginning of time, but rather the moment when a virtual universe became real, borrowing energy from the quantum vacuum that it has been repaying ever since through cosmic expansion. The power contained within quantum vacuum fluctuations might be accessible through advanced technologies that could manipulate the structure of space, time itself. Theoretical proposals for extracting vacuum energy involve creating negative energy densities or manipulating the boundary conditions that determine which virtual particles can exist in a given region of space. If vacuum energy could be harnessed, it would provide an effectively unlimited source of power that exists everywhere in the universe. A device the size of a coffee cup could potentially extract enough energy to power human civilization for billions of years, making all other energy sources obsolete overnight. Beyond the edge of our observable universe, beyond the most distant galaxies we can ever hope to see, lies something that dwarfs all the cosmic forces we have encountered. If the multiverse exists, our entire universe, with all its supernovae, black holes, and gamma-ray bursts, becomes nothing more than a single bubble in an infinite ocean of realities, each with its own laws of physics, its own history, and its own ultimate fate. In the eternal inflation scenario, our Big Bang was not a unique event, but one of countless explosions occurring continuously throughout higher dimensional space. New universes are constantly being born as quantum fluctuations trigger inflation in regions of false vacuum, creating an ever-expanding tree of cosmic domains that stretches infinitely in all directions. Each universe within this multiverse could have completely different fundamental constants. In some, gravity might be stronger or weaker, changing the formation of stars and galaxies. In others, the electromagnetic force might have different strength, making atoms impossible or creating matter with properties we cannot imagine. The strong nuclear force could be altered, preventing nuclear fusion or allowing elements that cannot exist in our reality. The total energy contained within an infinite multiverse would literally be infinite, making it the ultimate expression of cosmic power. Every possible configuration of matter and energy, every conceivable physical law, every potential history would exist somewhere within this vast ensemble of realities. The power to create infinite universes with infinite diversity represents the absolute pinnacle of cosmic force. Some regions of the multiverse might contain universes that expand forever, while others collapse back on themselves and big crunches that mirror their Big Bang origins. Still others might oscillate between expansion and contraction, creating cyclic cosmologies that repeat endlessly. The variety of cosmic destinies within a multiverse would encompass every possibility allowed by mathematics and physics. In certain interpretations of quantum mechanics, the multiverse consists of all possible outcomes of quantum measurements existing simultaneously in parallel realities. Every time a quantum event occurs with multiple possible results, the universe splits into separate branches, each containing a different outcome. This quantum multiverse would be constantly growing as new possibilities are realized. The anthropic principle suggests that we observe our universe's particular combination of physical constants, because only this combination allows observers like us to exist. In a multiverse containing all possible combinations of physical laws, conscious beings would necessarily find themselves in universes capable of supporting consciousness, no matter how unlikely such universes might be. If communication between different universes were possible, it could provide access to unlimited knowledge and resources. The technologies developed in universes with different physics might be incomprehensible by our standards, but could offer solutions to problems we cannot even imagine. The exchange of information across the multiverse would represent the ultimate expansion of scientific knowledge. The ultimate fate of the multiverse might involve the consumption of false vacuum regions by expanding bubbles of true vacuum, creating a cosmic selection process where only the most stable vacuum states survive in the long term. This could lead to a final state where all of reality converges on a single set of physical laws, ending the infinite diversity of the multiverse. We have journeyed from the quantum realm to the infinite multiverse, witnessing forces that stretch the very limits of what reality can contain. From the strong nuclear force binding atoms together to the possibility of infinite universes creating and destroying themselves without end. We have seen power expressed on every conceivable scale. The most remarkable truth we have discovered is that the universe does not simply contain power, it is power. Every atom in your body exists because forces beyond imagination hold it together. Every star that lights the cosmic darkness burns because nuclear forces convert matter into pure energy. Every galaxy spins through space because gravity and dark energy wage their eternal war across billions of light years. And perhaps the most profound realization is that we, as conscious observers, are not separate from these cosmic forces. We are their direct products. The calcium in our bones was forged in stellar explosions. The iron in our blood was scattered by dying stars. The gold in our jewelry was created when neutron stars collided in violent embraces that shook space-time itself. We are literally made of stardust, assembled by forces so powerful they can create and destroy entire worlds. Yet here we stand, conscious beings capable of contemplating our own cosmic origins, proof that the universe's greatest power may not be its ability to destroy, but its capacity to create complexity, beauty, and ultimately awareness itself. The universe has been working for 13.8 billion years to create the conditions necessary for you to exist. Every force we have explored, and quantum fluctuations to galactic collisions, played a role in bringing about this moment when you can understand your place in the cosmic story. What is the most powerful thing in the universe? Perhaps it is not any single force, but the universe's inexhaustible creativity, its ability to transform simple hydrogen into stars, stars into heavy elements, elements into planets, and planets into the stage where life and consciousness can emerge to contemplate the very forces that brought them into being. The next time you look up at the night sky, remember that you are witnessing the ongoing battle between cosmic forces that have shaped everything you see. And remember that you made of stellar ashes and quantum dreams are not just an observer of this cosmic drama. You are one of its greatest achievements. The universe's most powerful force may ultimately be its capacity to know itself through beings like us. In understanding cosmic power, we become the universe awakening to its own magnificent potential, then the full moon. Even from galaxies billions of light years away, the energy released in seconds exceeds what 10 trillion hydrogen bombs could produce if they exploded every second for the entire age of the universe. The most powerful gamma-ray burst ever detected. Nicknamed the boat for brightest of all time, it appeared in October 2022. It was so intense that it saturated gamma-ray detectors across the solar system and created detectable changes in Earth's upper atmosphere from a distance of 2 billion light years. Pictures standing on Earth and watching a flashlight beam from Alpha Centauri appear as bright as a car headlight. That gives you a sense of how impossibly powerful these events truly are. The light we detect traveled for billions of years, carrying news of stellar deaths from when the universe was young and stars were more massive and violent than anything we see today. Scientists have detected bursts so distant, their light began traveling when the first stars were being born less than 1 billion years after the Big Bang. These ancient beacons give us glimpses of the early cosmos when massive stars lived fast and died violently, seeding space with heavy elements essential for later generations of stars and planets. But compared to what lurks in the darkness between galaxies, even these titans pale in comparison.